Okay, good morning. Happy Friday. We have made it our first full week of this digital learning. Today we jump into the polar equation in calculus. Now, it's really important, these two ideas, especially this polar area idea. So I'm just going to wait to do the second half, the area part. And today we're just going to talk about slopes and tangent lines of polar equations, and we'll do area on Monday and Tuesday instead. That way we're fresh and recharged and ready to really commit to it, because it's really, really, really important that you can do both of these things. Alright, so to find slope of a polar function, so remember, a polar function is written, a polar ordered pair is r comma theta. So r being your distance from the origin, theta being your direction that you're angled. So when we graphed these things yesterday, when we had a variable in r, they create really cool kind of pictures, kind of spin them around. They can have little loops. They can get pretty crazy how they look. Here's a nice little peanut. So different kind of shapes, but they all kind of are like circles in their raw form, and then they're varying their distance from the origin, which is what's causing it to move in and out overall. So we talked about yesterday converting to rectangular systems from polar systems. So we know that x equals r cosine theta, and then y equals r sine theta. Now in these problems, the more complicated ones, r is not just a constant. R is going to be its own function. So r might be 3 plus 8 sine theta. It's not just going to be like a 4. And then r here is some function. So x equals r cosine theta, y equals r sine theta. In these AP FRQ problems, if you just write that down, you get a point. So make sure you know that. Today we're going to look at, finding tangent lines to these things, like we've been doing. So we need a point and we need a slope. Now to find the slope, this looks really scary. So dy dx is dy d theta over dx d theta. So change in x with respect to theta, and change in y with respect to theta, and change in x with respect to theta. So delta y over delta x, just like we've been working with. Now, this looks terrifying. Okay, but you don't need to have to memorize this. It's just the product rule. It's the derivative of the first times the second plus the derivative of the second times the first. So I don't even, like when I saw this morning, I'm like, wait, what the heck is that? I don't remember that. It's because I don't think about that at all. Think about what x is, and then derivative of x, it's just going to be the derivative of the first times the second plus the derivative of the second times the first. So it's just a product rule. Nothing crazier than that. All right, now they are always trig because it's r cosine theta and r sine theta. There's a lot of product rules with trig. That's just the way it's going to be. So write small on these, but maybe you're using blank notebook paper, so you got all the paper in the world anyways. We're just going to do two examples, and then I might show you a third one to help you with your homework, but just 3, and then we'll be done today. So determine the equation of the line tangent to r equals 3 plus 8 sine theta at pi over 6. Let's graph that. R equals 3 plus 8 sine theta. Alright, so here's my curve, and we're looking for its tangent line at pi over 6. Let's see if it'll graph. Show us where that is. Nope. Alright, so the first thing is we need to figure out, where on that curve is this tangent line supposed to be? So we need the point. So if we need a tangent line, we need a point, we need a slope. So we need a point. Well, my point is x comma y, because it's in the xy plane. So I gotta say x equals r cosine theta, and y equals r sine theta. Well, in this problem, r highlighted in yellow right there. So x equals 3 plus 8 sine theta, and y equals 3 plus 8 sine theta. Sine theta. R cosine theta and r sine theta. Alright, so I want the point, so I need to plug in pi over 6 for theta. So I'm going to get 3 plus 8. So you got to really know your unit circle. It shows up constantly. So the sine of pi over 6 is going to be 1/2. And then the cosine of pi over 6 is going to be the square root of 3 over 2. So that looks like 3 plus 4, which is 7. So 7 square roots of 3 over 2 for my x-coordinate. My y-coordinate, they're both sines, which is good because they're both a halves. 3 plus 8 times a half times a half. So that's just plain old 7/2. So there's my point. 7 square roots of 3 over 2, comma 7/2. So if I go graph that on my Desmos, so I got 7 square roots of 3 over 2. And then 7 over 2. Boom. So there's where on this polar curve I'm trying to draw a tangent line. That's the point. Now that's good. We can infer some things. Sometimes we'll get lucky and it'll be like at the top or where it's flat, and then you kind of just can write your answer. I do know my slope is positive here. So if you think about drawing a tangent line at that point, that purple dot, it's going to be a positive slope. So we can kind of problem shoot a little bit knowing that it should be positive. All right, so there's the slope. Next I need there's the point. Next I need my slope. So I need dy dx. So I need the derivative in the rectangular system. Well, dy dx is dy d theta over dx d theta. Now, this is x in yellow here, and this is y. So when I'm talking about dy d theta, I'm taking a derivative of that green function. Okay, so it's going to be a product rule. You could distribute it right away if you wanted. Then you're going to have sine squared, and some people mess that up. Or you could just product rule how it is. It's kind of a wash. It's whatever you feel more comfortable doing. But it is a product because you have this times that. So the derivative first is just 8 cosine theta times the second, which is just sine theta, plus the derivative of the second, which is cosine theta, times the first. Okay, so that's all dy d theta over dx d theta is going to be the derivative of that yellow thing. Same thing, it's a product rule. So the derivative first, which is 8 cosine theta, times the second, which is cosine theta, plus the derivative of the second, which is negative sine theta, times the first, alright, so that's a minus. So there's dy dx. It's a little bit of a mess. You could clean it up if you wanted. You could leave it there if you didn't. It's kind of, I don't know which way is better. Maybe it's up to you. Let's clean it up a little bit. So at the top, if you combine like terms, you're going to have 16 sine theta cosine theta plus 3 cosine theta. And then on the bottom, you're going to have 8 cosine squared theta minus 8 sine squared theta minus 3 sine theta. All right, so there's dy dx. Now, simple, right? So now I need the slope, so I need to do dy dx such that theta equals pi over 6. So I'm plugging pi over 6 into that. Gotta be really careful. So you got 16. I'm going to plug it into this version. Either one would be the same. So sine theta, so sine of pi over 6, maybe, so you could write down maybe the ordered pair at pi over 6 potentially, if that would help you. So it's square root of 3 over 2, comma 1/2. So sine of pi over 6 is 1/2. Cosine is square root of 3 over 2. Plus 3 square root of 3 is over 2. Over 8 square root of 3 over 2 squared. Minus 8 1/2 squared. Minus 3 1/2. Cleaning that up, looks like I got 8 square root of 3 over 2 plus 3 root 3 over 2. On the bottom, this is, so you're going to square the numerator and the denominator here, so that becomes a 3 over 4. So you got 8 times 3 over 4, or just those cross out, becomes a 2. So it just becomes a 6 minus 8 times a 4th, which is 2, minus 3/2. Never said it was easy. So 11 square root of 3 over 2 over, so I got 4 minus 3/2, which is 5/2. Outside, inside, keep, change, flip, whatever you want to call it. 11 square root of 3 over 5. That's my slope. Woo-wee. So now you can write your tangent line. So the tangent line would be y minus 7/2. So don't forget your point. There's your point, and there's your slope. So y minus 7/2 equals 11 square root of 3 over 5 times x minus 7 square root of 3 over 2. There's your tangent line. That seems crazy. Let's check it. Y minus 7/2 equals 11 square root of 3 over 5. X minus 7 root 3 over 2. Boom. So satisfying. Isn't that great? So yeah, this is really tedious. There's a lot of trig. But the process is very, very, very similar to parametrics in a way. And it's so satisfying when it works. It's very nice. Let's try another one. Now, they're always going to be trig, okay? Because by nature, when you're setting these things up, or cosine, you're introducing the trig to it. And they're generally trig anyways, because the trig ones are the ones that make the fun curves. So this one, so that's just straight up tangent line. This one says find the horizontal and vertical tangents, okay? So horizontal and vertical, same kind of idea. So I got R equals 2 minus 2 cosine. Whoa. That's not what I wanted. R equals 2 minus 2 cosine. I went ahead and just distributed the 2. So here's my picture. So I'm looking for where it's horizontal and where it's vertical. Looking at it, I see 3 vertical spots, and I see 2 horizontal spots, and I see a sharp point, which is going to be something we're going to have to talk about. All right, 2 minus 2 cosine theta. So step 1 here is I need the slope. So dy dx, dy d theta over dx d theta. So let's see, y equals r sine theta, and x equals r cosine theta. All right, so here we go. So dy d theta is a product rule. So we're doing it's going to be long. Drew the first, which is going to be minus 2 sine theta times the second. So I'm going to go ahead and write that as sine squared, plus the derivative of the second, which is cosine theta times the first. And then the bottom, so dx, x is derivative. It's derivative first. So minus 2 sine theta times the second, which is cosine theta, plus the derivative of the second, which is minus sine theta times the first. All right, cleaning that up a little bit. So the top becomes through the first times the second. It should be positive, because the derivative of cosine it's negative cosine, so its derivative is positive sine. I'd get there. All right, so when we now distribute all these things, we got 2 sine squared theta plus 2 cosine theta minus 2 cosine squared theta all over, looks like I got let's see here. Did it again. What am I thinking? All right, here we go. 4 sine theta cosine theta minus 2 sine theta. All right, there is my slope. Very good. So if this was a tangent line question, you would plug in. So if it said where is the tangent line at theta equals pi over 4, you'd plug in pi over 4. But that's not what it says. It says find the horizontal and vertical tangents. So now we got to remember what horizontal means. So horizontal means your left and your right. That means you're up and down. So your slope is 0. So you can think of it as make the numerator 0, because if the top's 0, the output's 0. So I'm going to make this 0. That also makes sense in that change in y being 0 means horizontal, because if you have no up and down, then you're flat. So dy d theta equals 0. Uh-oh. That's how I make this horizontal. So I'm setting the numerator here equal to 0. And suddenly, and without warning, our pre-calculus is back. We have to be able to solve trigonometric equations. Throwback to last year. It's pretty good stuff. So we got to be able to solve that. So looking at it, you could maybe pause if you wanted to think about it for a second. Ideas here. I would divide everything by 2 to get rid of those, just to make it a little easier. But then you can't solve it doesn't factor. I'm going to try to factor this, but I can't factor it when I have sine and cosine. So you got to use a substitution. So I'm going to replace sine squared. Use a highlighter. I'm going to replace sine squared with what sine squared is equivalent to with my Pythagorean identity. So sine squared plus cosine squared equals 1. So that means sine squared is the same thing as 1 minus cosine squared. So I'm going to replace that with 1 minus cosine squared theta plus cosine theta minus cosine squared theta equals 0. So then when you combine like terms, you get 1 plus cosine theta minus 2 cosine squared theta equals 0, which is going to factor. That's the same thing. Like, think of it as this: 1 plus x minus 2x squared. It's just a quadratic. If you don't love that they're all negatives, you could switch all the signs. Essentially, you're adding it to the right, or you're distributing a negative through. 2 cosine squared theta minus cosine theta minus 1, if that's more comfortable to you. If you'd rather think of it as 2x squared minus x minus 1. Now that's going to factor 2x plus 1, x minus 1. So this factors as 2 cosine theta plus 1 cosine theta minus 1. So I got cosine theta equals negative 1/2 and cosine theta equals 1. So potential solutions here. Well, here we are again. You gotta know your unit circle. So where is cosine negative 1/2? Cosine's negative 1/2 in quadrant 2 and quadrant 3 at 2 pi over 3 and 4 pi over 3. And then where is cosine 0? At 0 and 2 pi. Whew. All right, there's my horizontals. Now let's move over here and do the verticals. So vertical tangent means the slope is undefined, which means the bottom is 0. So dx d theta equals 0. So 4 sine theta cosine theta minus 2 sine theta needs to equal 0. Now this one's actually easier. You don't have to do any substitutions. You don't have to factor it by grouping. You can just factor out your greatest common factor. So I would just take out 2 sine theta. And what you're left with is 2 cosine theta minus 1. So I got sine theta equals 0, and I got cosine theta equals 1/2. So again, more unit circle stuff. So where is sine 0? 0 pi 2 pi. Where is cosine 1/2? Pi over 3. And 5 pi over 3. Next thing you have to do is evaluate your potential solutions. Oh, I got to sneeze. Hold on. Whew. The corona getting with me. All right. Now, what we see is there's some overlap here. So 0 and 2 pi seem to be showing up in both. That doesn't mean you made a mistake. That means that we have an indeterminate going on. If it's claiming to be both, then it's neither. So those are pretenders. 0 and 2 pi are got to go away. So my answer is my horizontals are going to be theta equals 2 pi over 3 and 4 pi over 3. And my verticals are going to be theta equals pi over 3 and 5 pi over 3. So if I look on my picture, what we're seeing, the reason there were two undefined, that was this point. So at 0 and at 2 pi, that's where this thing starts. It's a sharp point, so that thing is not defined. It's not differentiable. It doesn't have one unique tangent line. It has too many, so therefore it has none at all. That's what we see for the vertical ones, is this ordered pair that's like a little less than a half, comma 1, that spot, and then its reflection. Those are my vertical spots. And then also at pi. Yeah, don't forget pi. Almost left pi out. And then my horizontals, where it's flat, are at 2 pi over 3. And 4 pi over 3. All right. That's pretty much it. Really quickly, this is one of your homework problems. I'll go ahead and help you with it. Actually, the only thing is, I think you can do this. So finding the slope, we just did those. Here, just remember that this is your r, and then this is your theta. So what they're looking for is the slope right there. So they gave you the point. So their points in polar are more useful than the points in parametric. Because parametric, you had to work backwards and solve for t. But in polar, that actually hands you things, what you need. So we're trying to find the tangent line right here.